Swayam Prabha. Digital India. Educated India.
So now that we have learned how to draw NMOS transistor, how to look at the cross section of the NMOS transistor and the operation of the NMOS transistor in saturation as well as non-saturation region, I would like to show you how to do the same thing for PMOS transistor. So along with that, we will also do small signal models for both NMOS and PMOS transistor. At the end of this lecture, I will walk you through typical parameters for NMOS and PMOS transistor from the foundry that we get. And then using those numbers, how do you come up with some shortcut hand calculation numbers to be used all the time. We will start by drawing cross section of NMOS transistor, and then I will show you how to draw the cross section of the PMOS transistor. So please use your notebook and draw the cross section by yourself. I'm sure you're already familiar with it, but let's get started. So this is the gate region, N plus drain region and source region. And on the leftmost we have body or bulk connection. So this is the way our NMOS transistor looks like. Now we are going to do exactly opposite of this. We are going to change all the N's and P's to draw a PMOS transistor. And you would kind of start off in this fashion. You would say I would get the first diffusion, something like this. And this is the gate region for the PMOS. And this has to be P plus, and this is N plus. And you might say that, oh, I will start with a N type of substrate, N minus substrate. However, this is not possible because if you remember during the first lecture itself, I showed you a wafer, a single wafer. Now that single wafer is what you start off with, something like a P minus substrate, and on that you develop all these different transistors, right? So for developing a PMOS transistor, you cannot have yet another substrate. So what you do then is you create an island for the PMOS transistor as follows. I am intentionally showing you this so that you understand the concept. So we will be starting off with the same. We create an island using well diffusion that looks like this. So we still here also we have P substrate, and inside the P substrate first we lightly dope it with, so we call this N well, and inside the N well we create our PMOS transistor. Now you can see everything fits together. So this is our NMOS transistor and here is our PMOS transistor. So this would be the drain region for PMOS. This would be your source region and this would be your bulk connection. We also call that as well contact, and bulk over here is called substrate contact. Now this is something that as an electrical or electronics engineer you should be able to draw this in your sleep, in my opinion, because this cross section of a simple NMOS and PMOS transistor on the same wafer is what, you know, our entire IC industry, all the electronics that you're using, it's all based on this. You should be very conversant with it and you should be able to draw this on your own. Let's start doing comparison on the bottom now. I'm going to show you how to draw the symbol for NMOS and PMOS transistor. I'm drawing the transistor in a horizontal manner because that's the way the cross section looks like, and it will be easy for you to correlate to that. So in this case, we say this is our current flow, this would be your source region, this would be the drain region, and this would be your gate. And you show this line like this as a bulk connection or a body connection. So this would be our NMOS transistor. Similarly, we can draw PMOS transistor on the right. The symbol for the PMOS transistor looks like this. Center part is bulk or a well connection. In case of the PMOS, the current is flowing from this direction in this way. So source is denoted by arrow like this. This is the gate, and this would be your drain connection. Most of the students learn NMOS really well, but whenever you ask them to draw circuits with PMOS, they fumble quite a lot. Same thing happens when you get familiar with NPN transistors, but as soon as you try to draw PNP, you mess it up. I want to explicitly make sure in the classroom that we go through an example with PMOS. We did something like this with PNP as an example that's given to you so that you can practice on your own. Now in this case, we will go through the equations for both NMOS and PMOS. Again, this is kind of like mechanics, but you have to get used to it. You have to make sure you label the nodes correctly. You have to make sure the current directions are proper and things like that. Okay, so let's write equations for both sides. Again, I would like you to practice it in your notebook. So let's first draw how we are going to bias NMOS transistors once more, and we will draw the same for the PMOS transistor, and then we'll do the comparison. Okay, now let me describe the two diagrams to you. On the left hand side, we have NMOS, and if you note here, all the voltage sources, they are referenced to source. So we call it VGS, VBS, and VDS. Okay, and the current is flowing in this direction. So we denote it here as IDS. Okay, on the right side, here is a trick that I like to use to keep things simple. I simply, instead of calling it VGS, I like to call them VSG. And everything nicely falls in place in terms of equations and things like that. Otherwise, you have to deal with a whole bunch of negative signs here and there. Okay, so follow my train of thought here. In this case, we are calling the gate voltage positive plus minus as VSG. The bulk biasing is VSB, and source to drain voltage as shown here. Okay, and the current that is going to flow is going to be, in this case, is going to flow in this fashion, and we call it IST. Now we will write equations for both NMOS and PMOS side by side, and things will become clear to you. So first we will start with linear slash triode or non-saturation region. In case of NMOS, we know the condition for this is VDS is less than VGS minus VTH. And since we are doing both NMOS and PMOS, in this particular case, I will denote it as VTHN to denote the NMOS. And let's write the equation for this. The equation for this is given by IDS is equal to mu n Cox W by L, and then VGS minus VTH NMOS times VDS minus VDS square divided by 2. Now we will do the same thing for PMOS. As I told you before, we will simply change the suffix. We will flip the order of the nodes. So we will do VSD should be less than VSG minus mod of VTHP. The reason we are showing mod here is typically the threshold voltage for PMOS is shown as a negative number. So in order to reduce that confusion, we just take mod for whenever we talk about the threshold voltage of the PMOS. Okay, and in this case, the current equation is going to be IST equal to mu P Cox W by L of the PMOS device times VSG minus mod of VTHP times VST minus VST square divided by 2. So this is the equation comparison between NMOS and PMOS for linear, triode or non-saturation region. Now let's write the equation for saturation region. So when is the transistor is in saturation region? Saturation region is when VDS is greater than equal to VGS minus VTH of NMOS. Similarly, on this side, we will call it VSD is greater than equal to VSG minus mod of VTHP for the PMOS. Saturation region equation for NMOS is IDS is equal to mu n Cox W by L times VGS minus VTHN square, and there is a divide by 2 here, and the channel length modulation effect is 1 plus lambda n VDS of the NMOS device. Okay. And for the PMOS device, we can write it up as ISD is equal to mu P Cox W by L divided by 2, and then VSG minus VTHP mod square, and then you have 1 plus lambda P VSD. That would be your channel length modulation part. So this is summary of both NMOS and PMOS operation on a single sheet. Most important thing to remember here is this is a large signal behavior. Okay, so everything we are talking about here is a large signal. Now we will take the next step, which is to come up with small signal model for MOSFETs. For most application, the bulk is generally connected to the source and we don't explicitly show it. So we will be starting off with a simple schematic like this. We like to use the transistor in saturation region. So what is really going on in saturation region, as we saw earlier? In saturation region, if I change the gate to source voltage, small amount, then we see a change in the drain to source current. Now this is very similar to what we saw in the bipolar transistor, where we changed the base to emitter junction voltage and you saw a huge change in the collector current. So something similar is happening here. And if you remember the analogy that I had given to you earlier, where you have a pipe which is carrying, a large diameter pipe which is carrying a lot of water, and just by changing the tap by hand with a really small deviation, you are able to change the flow of the water between one side to other side. Okay, so something similar is happening over here. By changing the gate voltage, we can change the drain to source current. If we change the VGS up or down, then we get IDS that goes up and down, and that's what we desired. Again, here you can see that this behavior looks like a transconductance, and we call that GM. So let's figure out what the transconductance is. We start off with the basic saturation equation. IDS is equal to figure out the transconductance, we would like to take a derivative of this current with respect to the gate to source voltage, because gate to source voltage is what we are changing, and as a result of which we are seeing change in the drain to source current. the transconductance Gm is given by is equal to del I ds by del VGS when we keep VDS constant, and you can immediately see this is going to be equal to mu n Cox W by L times VGS minus VTH times 1 plus lambda VDS. Now we can take a next step where I can multiply this expression by reciprocal of VGS minus VTH, and then I make a square here and I can divide this by 2 and I can multiply by 2. The same expression, and quickly you can figure out that hey, this is nothing but IDS and then 2 IDS divided by VGS minus VTH of the device. So this is our first expression for the GM of the transistor, MOSFET transistor. Now this expression is exact expression, and in a few minutes you will know why I call it exact, because this includes the channel length modulation effect. So what this is telling me is that if I know what the drain to source current, DC current flowing through the transistor is, and if I know the gate to source DC voltage, then I know what is the transconductance of the device, GM. We can also write a different expression for GM. Let's simplify things a little bit. We'll call it Kn as mu n Cox W by L. IDS is equal to Kn divided by 2 VGS minus VTH square. In this particular case, I'm going to ignore the channel length modulation and see what we get. GM is equal to del IDS divided by del VGS, that is equal to Kn times VGS minus VTH. And we also know that from this expression, VGS minus VTH is equal to 2 times IDS divided by Kn, square root of that. So we can substitute and we will get GM is equal to Kn times square root of 2 IDS divided by Kn, and this can be written as 2 IDS times Kn, square root of that. So now we have 3 formulas. Let me highlight them. This is one formula for GM. This is third formula for the GM, and we already have one formula here. The way to look at this is the transistor drain to source. There are 3 components deciding the behavior of the transistor. One of them is IDS, one of them is the W by L parameter and mu n Cox, and the third one is VGS. If you know 2 of them, that's good enough to figure out your GM, and you can use different forms of GM depending upon what you know out of them. And we would use the form which is convenient according to the application. The form number 1, which is shown over here, is the exact form, because in this case we have taken into account channel length modulation. In the form number 2 and form number 3, we ignored the channel length modulation to figure out the GM. And for hand calculation purposes is close enough. The values that we are going to substitute here, the IDS and VGS, they are our DC operating point. That is a key thing you have to remember. And GM is a small signal parameter that we are calculating. Okay, so we are calculating small signal parameters using large signal operating point information. Let's compare this to our friend bipolar transistor. If you remember, bipolar transistor has only single form. And what is the bipolar transistor form? Is GM is equal to IC divided by Vt. IC is the collector current and Vt is 26 millivolts, kT over Q. Okay, these two we can compare with each other in terms of the transconductance of the device. We are going to go into that a little further for comparisons, but this is just a starting point. So based on this, what we know, just this is the model, small signal model of our device is going to look like this. So from drain to source, we have a current flowing, which is Gm times VGS. Note this V is the voltage at the small signal voltage at the gate for this purpose. Okay, and Gm we calculated based on, for example, 2I ds divided by VGS minus VTH. So IDS and VGS, they are large signal or DC operating point information. Well, this is a very simplistic model. If you look at the transistor equation, IDS, we have change in the current due to drain to source voltage change, and that we can capture by taking a derivative IDS with respect to del VDS for fixed VGS, and that would be given by Kn divided by 2 VGS minus VTH, because this is a fixed quantity, and multiply this by lambda of the device. So we say that this is approximately equal to lambda times IDS, since this part is almost same as large signal IDS value. The output resistance now, R out, that is equal to reciprocal of this quantity, which is del IDS by del VDS, that is going to be equal to 1 divided by lambda IDS. Again, IDS here is a large signal or DC operating point, and this R out that we have is a small signal output resistance. What this is telling us is, if you increase the current IDS, DC operating point current, then our R out small signal output resistance will reduce. Also, it's telling us that if I increase the channel length, if I choose a device with larger L, then what does that do? That will reduce our lambda. This is from the previous lecture, and as a result of which you will get R out, which is going to increase. And this is all making sense as we discussed earlier. Okay, so next level of the model is going to look like this. We have GM-VGS, and the next thing we are going to add on top of that is going to be resistance. Here, R out, which is equal to 1 divided by lambda IDS. So far we have discussed so many different things about the MOSFET, but all these things we have talked about, they are in equation form. You really need to have feel for numbers. So I'm going to give you the model numbers that you will find in a SPICE card, model card for a 0.5 micron CMOS technology. And again, this is an example. These numbers do not represent a particular foundry, because all these numbers from each foundry, they are confidential. So I'm kind of using average values to give you a perspective about what these numbers mean and how do you calculate the different coefficients that you need to do hand calculation. Let's get familiar with all these terms. VTO, which is threshold voltage. For NMOS transistor, I'm just picking up typical values. 0.5 volts. For PMOS transistor, minus 0.6 volts. and unit over here is volts. Gamma, which is body effect coefficient, is for NMOS transistor is 0.45, and for PMOS is, let's say, 0.4, and the unit here is square root of volt. Tox is thickness of the oxide. Angstrom is 10 to the power minus 10 meters. Okay, and in this case it is 90 angstrom. And again, the same gate oxide is on both sides, so this is what it looks like. U0 is the mobility. In case of NMOS is the mobility of electrons. In case of PMOS, it's the mobility of holes. For NMOS, it's 350, and for PMOS, it's 100. Unit is cm square per volt per second. Lambda, which is the channel length coefficient. In case of NMOS, it is 0.1, and in case of PMOS, it's 0.2. And the unit here is volt to the power minus 1. Important thing to note about lambda, or the channel length modulation coefficient, is the number lambda which is given to you in the data sheet is for the minimum channel length. This 0.5 micron tells you the minimum channel length you can draw in this particular technology, and the value of lambda is given for that particular number. Okay, and I'm going to explain it to you as we go forward. 5, the number in the model card is giving you 2 times 5f. In case of NMOS, it's 0.9. In case of PMOS, it's 0.8, and unit is volt. Okay, so this is what you will find out from the model card for a technology from some foundry, right? So these numbers by themselves, every time you cannot start with these numbers. So I like to use some intermediate calculations which are easy to wrap your head around. So let's go through that calculation. For example, Tox by itself, 90 angstrom. Every time we cannot substitute that number everywhere, right? So instead, what's more useful for us is the oxide capacitance, Cox. So Cox is given by epsilon ox times epsilon naught divided by Tox. I'm going through the calculations laboriously right now, because the first time you should go through that to get a feel, and then later on we can use some ballpark numbers for quick calculations. Okay, so epsilon oxide is 3.97 multiplied by epsilon naught is 8.85, 10 to the power minus 12. Units are important. The unit here is farads per meter, and Tox is 90 times 10 to the power minus 10, and this is meters. So this number is going to come out to be 3.9 10 to the power minus 3 farad per meter square. Again, the unit farad per meter square, it's kind of difficult to use. So we like to convert it to the numbers that we use on a chip, right? For example, it's a lot more realistic to use micrometer and femtofarad. Femto being 10 to the power minus 15. We can say that Cox is equal to 3.9 10 to the power minus 3 multiplied by 10 to the power 15 and divided by 10 to the power 12. So this would be our femtofarad per micrometer square, and you can quickly then get a number which is 3.9 femtofarad per micrometer square. Now this is very useful number, because whenever you draw a transistor, let's say you drew a transistor with width of 10 microns and length of 1 micron, and we would like to figure out the capacitance of this transistor, the gate capacitance. And here we have a quick number that we can use, which is 10 times 10 micron square, multiply this, and it will be 39 femtofarad that we can use. So this is the reason we like to use these units in this format. Next thing we will play with is the channel length modulation coefficient, lambda. As I had described to you earlier, lambda n in this case is given by is 0.1 volts to the power minus 1. However, it is given for channel length of 0.5 micron. So this is 0.1 volts to the power minus 1 for 0.5 micrometer. L is equal to 0.5 micrometer. So if you are using a NMOS transistor with different channel length, then how do you compute lambda for that particular transistor? And a simple formula is, we know that as channel length increases, lambda will reduce. So the formula becomes, generic formula becomes lambda n is equal to 0.1 multiplied by 0.5 micron divided by L's of n. And that would be equal to 0.05 divided by ln volts to the power minus 1. Here ln is given in micrometer to remember. So this is the formula that you would use to quickly compute. Let's say if the channel length of the transistor is 5 micron, then you can quickly tell that our lambda has dropped down by an order of magnitude to 0.01 volt to the power minus 1. Similarly, we can say lambda p is equal to 0.2 volts to the power minus 1 multiplied by 0.5 micron. That's the smallest feature, smallest channel length that you can have, divided by L's of p. That is equal to, here again, 0.1 divided by LP volts to the power minus 1. And you just have to simply substitute L's of p in micron. The next useful number to compute your drain current is K value, and that is given by, part of that is given by mu n Cox. So we know that mu n is 350 centimeter square per volt per second. Multiply that by 3.9 femtofarad per micrometer square. So we can unravel the units and it will look like 350 10 to the power minus 4 multiplied by 3.9 10 to the power minus 15 divided by 10 to the power minus 12, and this is going to be amps per volt square, and that is, the number is going to, again, since this is amps is not very useful. Our favorite unit is microamps for doing design on a chip. So we will reformulate this, dividing by 10 to the power 6, and we call it microamps. Sorry, minus 6. And this is going to come out to be equal to 136.5 microamps per volt square. So this is something that you can use in your saturation equation quickly. For example, if you have mu n Cox W by L divided by 2 VGS minus VT square, then you know this number, you know ratio of W by L, and you immediately know the current in microamps. So it's a very good thing to do for your hand analysis. Okay. And we can do similar expression. You can do it for mu p Cox, and you can convince yourself the value is 39 microamp per volt square. We'll stop right here.